Hello, and thank you for attending. We are going to be talking about conditionals inside of subassembly composer. Simply if-then statements that are going to make your subassemblies hugely more efficient and powerful. These are something that I see underutilized kind of chronically inside of Civil 3D. It's an incredibly powerful tool. It's a little bit cumbersome, and I think it gets skipped over a lot. So I'm excited to share this with you. I think it's something that a lot of people who are corridor modelers can really get a lot of benefit from. My name is Justin Konen. I work for a small consulting firm based out of St. Paul, Minnesota called Isthmus Engineering. I have over 10 years experience in civil design. All of that has been inside of Civil 3D, working on almost exclusively large-scale mega projects, LRT, BRT projects, using Civil 3D and Subassembly Composer. I am also a former computer programmer for a couple of years, despite not having a computer science degree. Spent a few years being a computer programmer, and I think it's part of the reason that I love Subassembly Composer so much. Really lended itself well to making some of these custom ones. I've led the modeling efforts on multiple large-scale infrastructure projects, and particularly when I started, there was not acceptable subassemblies for rail design that were available out of the box for Civil 3D. They have come a long way for it, and maybe if we were then where we are today with what was available out of the box, I might not have needed to have dove quite so deep into Subassembly Composer in the past, but I've spent a lot of time making custom subassemblies for these projects. I also teach Civil 3D classes to cities, counties, and to consultants. Minnesota uses MicroStation, unfortunately, for me. For it, Wisconsin, you guys are lucky to use the what I consider to be the superior program. And I'm currently the civil design lead on the Purple Line BRT project, continuing to kind of advocate for some of these streamlined, efficient corridor modeling approaches. So just a quick overview of what we're going to be working on here. We will be spending most of our time in Subassembly Composer itself here as we're going through. I will try to keep the PowerPoint presentation as brief as I can while still trying to lay the groundwork. And I think it's just a little more interesting if we're able to use the program itself. I am assuming that the people that are watching this have done corridor modeling at the very least. If you've never actually opened Subassembly Composer, that's probably all right. You might be a little bit lost as to some of the specifics and might feel a little bit fast, but you should be able to keep up if you at least understand what a subassembly is and have used those inside of corridor modeling. If you haven't ever done any corridor modeling, this class might be a little bit difficult to try to keep up with, just because you're not going to be understanding what it is that we're going for with it. But if you've never opened Subassembly Composer, stick with me. It should still work out fine. If you have used Subassembly Composer, we're going to get real nerdy today. So we are going to run through multiple different examples. I have more queued up than we possibly have time to get through here for it, but hopefully we can get to enough to show some of the power that is available inside of Subassembly Composer when it comes to conditionals and if-then statements. When I teach classes on this, I do try to do all of the examples live from scratch and have people follow along. This is too short of a presentation to be able to do that, unfortunately. So I do have a lot of the examples kind of queued up and with different save points. So we'll kind of hop forward a little bit quickly through a couple of these to try to cover as much ground as possible, make sure that people get a little bit of exposure to all of the different types of conditionals that we can run through. I will also say that the examples are greatly simplified due to time constraints for it. So all of these are a little bit stripped down from what you would actually use inside of a corridor model on a project for it, but they are all going to be fully functioning subassemblies for it. They're just simplified a little bit to make it easier to follow. There's other aspects that I would say are best practice for subassemblies that are kind of skipped here to keep things a little more compact. Nothing that should alter the understanding of how to use conditionals. So what is Subassembly Composer? It is a automatically installed custom subassembly tool. Basically, if you have Civil 3D installed on your computer, you also have Subassembly Composer. I think it could probably be disabled by someone's IT department. I haven't seen a company that's done it yet, but it tends to just come along and be there. It is a very simple tool. We'll take a look at it in a little bit. Basically, you can pull it up on screen and you can see everything that you can do just right there. There's no deep menus. There's no super complicated things. It's pretty simple. That being said, it's surprisingly powerful, and you can do almost anything that you want with it. Um, it is, however, pretty non-intuitive. I would argue it has a terrible user interface, particularly as things start getting more and more complicated for it, and it's not terribly well documented. So if we jump over to Subassembly Composer here, we have it up with just the world's simplest subassembly right here. This would be basically just a little schematic curb that you could drop in. So if you were building an assembly and this was one of your assemblies, you'd simply be placing the lip of the curb as the insertion point. You see point P1, we'll talk briefly about point numbering later on. And all you do inside a subassembly composer is pull points on from the side here in a flowchart condition. So the whole thing is a flowchart of programming. And you simply work your way around from point 1 to point 2 to point 3, etc. And then as you do that, you add links between the points, and that is the whole system. That's everything. You can get more complicated about how you set the points, whether they ride along with targets or not, whether they do some math before they actually get placed. But really, this is the whole program. You see, it is pretty simple and streamlined. So, pretty amazing what you can end up getting it to do. So, just to take a quick look, not something we'll probably be covering today, but we can take a quick look at a much more complicated subassembly. So this is a subassembly that has multiple different targets, both for different offsets, where the wall is placed, where the footings land, the bottom of the wall, all of the excavation and quantity units, different surfaces to target. This very, very rapidly goes through and builds very flexible walls inside of your corridor to use, particularly for high-level cost estimates early in projects. Use this one a lot. You can see this has a lot going on. Pretty streamlined. There's actually a lot of conditionals stuck inside of this, inside of these different ones here for it. But I just wanted to show people quickly that we're going to be talking a lot about some pretty simple subassemblies that are, just curbs, just really simple retaining walls, and I wanted people to be aware that you can go quite deep with this, and you can solve almost any issue that you have inside a corridor modeling. So this is what Subassembly Composer is. So despite it being pretty poorly documented and having to figure out a lot on my own, especially when I started out about 10 years ago with it, it is my favorite part of Civil 3D. I think it's just a blast to work on, and anytime I see a problem that crops up with a corridor where I go, oh, I can make a custom subassembly for this and it'll save a bunch of time, I get really excited. So now we're going to jump over to the meat of the presentation here. What are conditional statements inside of Subassembly Composer? So hopefully you can stick with us now with that introduction, even if you haven't used Subassembly Composer before, and if you have, I apologize if you glazed over a little bit there. We're going to be getting into the new stuff right now. So conditional statements in Subassembly Composer they're just programming statements. They're if, then, else statements. If you are an engineer, you certainly had to deal with these in college, in some of your programming courses or some of your analytics courses. If you're not an engineer, very likely that you've done something, nearly as complicated, at least inside of Excel. It's that type of stuff, and just being able to use these conditionals really opens things up. There's three types of conditionals inside a subassembly composer. There's decisions, which are kind of the base one for it. It's a very simple if-then statement. You write a statement, and if it's true, it follows a flowchart one way, and if it's false, it follows it another way. There's a switch, which is kind of nearly the same thing, except that you can have multiple different outputs coming out of that switch. And then the one that is very rarely used, but probably should be used a lot more, is a variable write, where basically you can write a if-then statement using Visual Basic as the language, and define a variable to be whatever you want it to be inside a subassembly composer. And it's actually a very powerful way to do things, to be able to do stuff that has a lot of different options associated with it. We are going to save that one for the end. It's a little more complicated and it's a little more nuanced. So if we get to that, that means we're doing good on time. One thing to note with these is that as your corridor is building, it checks these conditionals every frequency point. So as your corridor is going through and building every 25 feet or whatever you've set your build rate to for it, it checks, am I above or below existing ground now? Continues with the conditional, builds what it needs to, and then the next frequency point, it resets and starts over. So that's really what gives it the flexibility and dynamicness as the corridor is building. But just be aware that it does run through these conditionals every single frequency point along the corridor. It's not an issue in terms of building the corridor in any way, in terms of like time or processing power, but we do need to be aware that it gets reset and ran every single frequency point on the So if as we're diving into this, as I said before, some of the examples are really simple. Maybe a little overly simple for what you would actually use inside of a corridor. So if you're looking at this and wondering, well, what can I actually use these for? Because these samples aren't something I maybe would necessarily do. This is just a quick list of just some of the things that you can do with the conditionals. First one is a really helpful one, and that's multi-targets. There is nothing out of the box that you can select more than one target for. With any of the subassemblies here, and multi-targets are pretty easy to do inside a subassembly composer. So you could set it so that it's looking for 3 or 4 different targets, and it'll find and target either the nearest or the farthest target in terms of offsets. We have conditions all the time where we want to be able to target multiple surfaces. So we have a condition where we have our existing grade surface that we get back from our surveyors, and then we end up getting, say, a muck surface that has to be pulled out and remediated before we can do any work. And then we want to be able to go by and dig out our datum surface below whatever is still there. Well, what that means is you want to be able to target the lowest surface. So that if the muck surface is there, you dig down to the muck surface or you don't dig down, it's already open out in the field there. You don't need to quantify that for it. But if the muck surface isn't there, you want to be able to just go to the existing grade or a distance below the existing grade. Being able to target whichever one of those is deepest or whichever of those is shallowest is something you just simply cannot do with the out-of-the-box subassemblies, but is trivial to do inside a subassembly composer. You can make your retaining walls automatically flip back and forth to cut, so you can get the batter on the right side. You can have the toe and heel expand correctly, automatically. This is incredibly helpful if you're looking at alternatives and you just want to be able to, run a wall through if there's, greater than a 3-foot drop for it either direction, and have it kind of just put the wall in automatically, show the grading limits. You can have super flexible ditches. Also, selectable subassemblies. They're very, very difficult, perhaps impossible to do with some of the out-of-the-box subassemblies, but with Subassembly Composer, we can make it so that every curb that your state has a plate for, that your county has a plate for, is selectable from a drop-down from the same subassembly. Another powerful one that we unfortunately will very likely not have time to get to is the fact that subassemblies can talk to each other really powerfully. So inside a subassembly composer, you can make it so that, say, the pavement thickness from one subassembly can be used as an output to go into a different subassembly and have everything just kind of match. We have a whole set of custom subassemblies that talk to each other, and if you change one thing, it ripples through the entire assembly all the way to the end for it. It's an incredibly fast way to make changes on projects. So we're going to try to take a schematic look at the way that a lot of these subassemblies are arranged and the way that we want them to be arranged. So right now, if we had a schematic of a very simple subassembly, it might look something like this. We start at the insertion point, we add a bench, say off the back of curb, a little 2-foot flat spot before we break and start grading to existing ground. And then when we hit existing ground, we add a ditch. This would be a very, very simple subassembly to be able to put together inside a subassembly composer. As an example, it's probably pretty poor because we could use the out-of-the-box subassemblies and not lose any functionality. But let's say we wanted to add a conditional to this. Do the same thing. We add a bench, we grade to existing ground, and then we check if we're above or below existing ground. We might be grading up, might be grading down. We add a small swale if we're above ground, and we add a full-blown ditch if we're below ground. So this is the type of sample you can find all over the internet. It's the type of sample that AutoCAD uses in their downloadable sample for it and their tutorial that they have packaged up with Civil 3D. And it's a fine example, but it's so simple that it's hard to understand how you're supposed to expand on this. The other thing is that it's at the very, very end of the subassembly, and almost all the samples show it like that because it's really easy to show that as an example, but it really, really limits what it is that we actually are trying to do with these. So a lot of times people will start with this, and then they'll figure out after they start using the subassembly, well, you know what, I really actually need a variable bench for it. So they start at the beginning and they check, is it less than 4 feet above existing? If so, we're just going to add a 2-foot bench, but if it's more than that, we actually need a 5-foot bench for perhaps safety reasons here. Now, adding this at the start means it branches right away. And I have seen just dozens and dozens of examples of good qualified people who know how to use Subassembly Composer making the rest of their subassembly like this. They essentially copy the rest of it to each one and follow through. So you see this branches pretty quickly to 4 different ending conditions, 4 different things that you have to keep track of for it, and a lot of different areas that we're going. Now, what if we wanted to add another conditional to this? We wanted to be able to see how far away the right-of-way was, do some quick math to see if we can make a steep slope fit or a shallow slope fit, or we have to use a steep slope. Well, we'd want to check one and then the other and then the other or the other. And you can see here, these can get away from you really, really quickly as you try to add on some pretty simple stuff into a single subassembly. I've seen these a lot. I've opened up subassemblies before where people have just hundreds of branches spread out. It's almost impossible for them to be able to track anything down. If it builds weird inside of Civil 3D, it's very difficult to troubleshoot. So this is the issue that we're trying to solve. It happens a lot. There's not a lot of great examples for it. What we want is we want all of these to come back together. So we still want to be able to use multiple conditionals throughout, but we want them to come back together afterwards. So we want to be able to check, do something, or do something else, and then come back together before we check again, before we add some other stuff in there. So just to reiterate, this it does exactly the same thing as this, but there's so much less to keep track of, so much less to label, so much less to troubleshoot if something builds weird. All right, so on the screen, we have one of the Civil 3D supplied sample subassemblies. So they have a quick tutorial online on how to use switches, decisions, which is the if-then statement inside a subassembly composer. And this is the sample file that goes along with the tutorial. You can find it online. Basically, it's just a really simple little sample. From the very start, we start at the insertion point, go over for a flat spot, and go down to point P3, and then we check inside of here whether point P3 is below or above the existing grade. There's a couple ways to check that. But right here we see that the Y value of point P3 is greater than the Y value of auxiliary point 1. We'll talk about that in a moment. If this is true, we are in a fill condition, and it builds point 3 and point 4. And if it is not true, it builds point L3 and point 4. And if that is not true, we are in a cut condition and it creates a ditch and comes back up to existing grade. This is a very, very simple one for it. So this is a fine thing to use as an introductory example. It's also not very helpful. There's not a lot of spots where you have a decision simply right at the end of the subassembly. It's more common to get them in the middle, and I would say the most common to have them at the start. And this doesn't prepare you for that at all. It actually kind of sets you up to make really bad subassemblies. Just to talk quick about some of those, we can open up a different subassembly for. We'll open that curb one back up that I had open. Not that one, apologies. Open up that curb one that we had before. Again, this is an incredibly simple subassembly. It's basically we just drew a closed shape and then added a shape to the end for it to fill that in. And if we brought this inside a subassembly, inside of Civil 3D, wouldn't be able to do anything with it. So if we did want to add a really simple conditional, something that people often want out of a curb subassembly is being able to change where the insertion point would be on one of these subassemblies. So if we wanted to, we'd maybe be able to click it on to use the lip here to be able to put it on the end of a pavement section. That's probably the most common way that you would insert a curb when you're building a corridor, as we build off of center lines a lot. But there's a lot of value to be able to place that off the back of curb if you're building from a sidewalk towards the middle. That happens a lot when you're doing an ADA reconstruct. You want to be able to build from a building face over to the center line and figure out where the center line is going to be. You want to be able to connect to the back here. So what would happen if we wanted to be able to connect to the back? And this is a spot where I'd normally do it live if we were in a class and add these, but I do just have this prepared here for it. So we'll try to step through some of these. Now, this is just the next step. I do want to point out this is what I'm going to say is wrong. The wrong way to do this. We're going to work through that first. I see this all the time. So I work with a lot of other consulting firms, and I teach a lot of classes for it. And I get tasked with troubleshooting other people's subassemblies a lot. And you see something like this all the time, where you start, you hit a decision, and you go off down one row until the end of the subassembly one way, and you go off down another area until the end of the subassembly the other way, and you basically have two completely separate subassemblies in every way for it. They happen to be in the same file. You happen to be able to insert them the same for it, but it splits. So we'll take a look at this. We'll look at what it's doing right now, and then we'll take a look at how to fix it. So what we have here is we've added a output parameter called insertion point, and it's just a drop down. And you can choose either lip or gutter with this one for it. So right now we're at the lip, it's at the lip point. If we go to gutter instead, we see that it goes to the flow line. In a little bit, we'll add another one for back. So if you take a look at this, this does work. If you bring this into Civil 3D, it'll come in fine, it'll insert in the correct spot, and it'll build. So in some ways, this works fine. However, a couple different things are going on here. One is that we have way more clutter inside of this than we want, and if we need to change something, it can be really, really difficult to track it all the way through and do this, particularly if there's ever a spot where you start adding multiple conditionals. So let's say that we wanted to be able to choose 3 different insertion points, and we wanted to be able to also choose the face of the slope there. You would have a conditional for all 3 of those, and then under those you would have another conditional, and this starts branching and turning into a huge tree very quickly with a subassembly that feels like it shouldn't be very complicated. So we definitely want to avoid that and keep things simple for ourselves and for anybody else who's going to use our subassembly. The other one, which I would argue is even a bigger problem, is that if you do end up branching like this, you end up having different numbers associated with these points. So these points, you can't see them inside of inside of Civil 3D. You're only going to see them inside of Subassembly Composer. These are different than the point codes that you get inside of Civil 3D. These are exclusively just for construction of this. But if you note, this has point P4 up at the top, over on the right here. And if we switch to the other leg of this flow chart, this workflow through here, we see that we have point P10 up here. What this means is that if you attach another subassembly to this point up here, and then you change the conditional, or you made a conditional that automatically fired as the corridor was building, say it switched from a cut to a fill, and it switched, and that point switches, the subassembly that is attached to this point can't figure out where it's supposed to go to, and it will snap back to the origin of the previous subassembly. So it essentially fully breaks your corridor by having these points be different. And again, I see this all the time. Now, there's 2 things. So one of these is just a best practice, which is that you cannot rename a point inside of one of these to be the same. So I could not rename point 4 to be the same as point 3 because that point value has already been used. However, if we are on a completely different path and we're on a different branch, Subassembly Composer is okay with that. So we could actually go through and rename all of these points to be the same. So P7 the same as P1, P8 the same as P2, etc. all the way through. The big one, it would be point 10 or anywhere that we think we want to attach things to. So now if we look at maybe some next steps for this one, what would happen if we wanted to be able to attach this in 3 different spots? Well, it starts getting even more complicated with these. The numbers get even weirder, and we'd have to manually go through and rename or renumber every single one of these to match all the way across. And if anything did change, we wanted to add something, we wanted to add maybe a mod knockout to the back of the curb for paving stones, some of those types of things. Particularly the one that we could turn on or off. I think maybe you can see now how this can start sprawling and getting really uncomfortable really quickly. So instead, what we want to do, we'll come back to that one. That's just a way to do it with a switch instead of 2 conditionals. Instead, what we want to do is have our branching subassemblies merge back together after we make the changes. So let's step through this and take a look. Right away, we start at the very beginning, and we're going to take a look at this decision and see what it does. The first thing it's doing, it's checking if the attachment point, which is that variable that we created earlier, a parameter, sorry, that we created earlier with the variable name attachment point, is set to lip. If it is set to lip, it follows the true label, which we've labeled as lip to make it a little bit easier for ourselves to follow, and it uses this point P1. If it's not set to lip, it goes over to this next decision. It takes a look, and is it set to gutter? If it is set to gutter, it follows this decision point and goes to this point P1, which we'll take a look at in a moment. And if it's not set to that, that means it must be set to back, and it follows this point P1. So all we have here is that the point P1, the first point in the subassembly, is at the origin, and it is over 0x in the x direction, and it's up 0 in the y direction. So that is our base spot, and it comes in right at the insertion point. If we did want to change the insertion point, and we want to go to the gutter here, we want all of these point numbers to stay the same. So we basically want to take point P1, which everything else is built off of, and we want to shift it over and up a particular distance. So what that means is that we want to shift it over the gutter width. So remember, the insertion, or the red point is always the insertion point on subassemblies, no matter what. You cannot change where that red crosshairs is. You can only change where your points are in relation to it. So we're taking all of these points and we're moving them over, which is why there's a negative sign here. We're going to go over the gutter width, which is, this is a B624 curve, so we go over 2 feet. For that 24 inches, we're going over the gutter width, and we're going up the gutter width times the gutter slope. So we go over and up, and that pushes that insertion point over and down. So this is where it's going to come into Civil 3D. This is the insertion point where it would attach to either another subassembly or to our initial assembly point. If we go to this point P1 at the back, we see that we need to push it over and down. Which means, I guess, really the way to think about it is that we're pushing it over and then kind of up with that. So we go over the gutter width, the slope times the height, and the head width to get over to that point, and then we go up the gutter width times the gutter slope, and also the height of the curb. Now, if you notice, I don't have any numbers in here for the most part, besides throwing a reciprocal in there. And I am a big advocate for, as a best practice, to never put any numbers inside of any of these points, almost without exception. If you have a number, give it a variable name and put it out here, because there is always a chance that somebody is going to want to change that. And if you ever have a number hard-coded in here and you got to go back in and change it and then re-import the subassembly, you've made your subassembly a lot worse, and there's almost no reason to do this. Now, it does drive a few people nuts that when they bring in one of the subassemblies I've made, there is a lot of parameters associated with it, but you hardly ever have to change any of them, and you always have the option to. So now we have a subassembly, and I want you to kind of take a look at this one and compare it to the last one here. Even if we had numbered everything so that it didn't drop any attachments points from it, this is just hugely more compact. And this is the thing that I think is often overlooked in a lot of the tutorials and attachments, and this is converging subassemblies. We go out, we do a conditional that is checked on at the decision point. It goes and it creates the points that are all parallel and can be named the same. And then after we're done with that, we go right back into the same flow after that, and we have one continuous shot here of points that are very easy to modify in the future, is very easy to check. It's not something we have to do 3 times. We'd have to copy paste this over and draw a bunch of arrows. We didn't have to renumber a bunch of things. And you can always converge back together as long as you never end up with the same point number. So if you're ever doing this and it doesn't let you draw it, the same point number is somewhere in the same line. You can always converge back together as long as you have unique point numbers inside of any subassembly. So right here is one of the simplest things that you can do with conditionals inside a subassembly composer for it. And that is basically we're checking a variable that we made, and we're placing that point at different spots, and this makes it that we have a more flexible version of the curb subassembly. I'm going to now ask the person who's controlling the recording to pause for just a moment here and see if there's any questions that we need before we continue with some more involved examples. All right, we're going to go through one final, more complicated example here. So we're going to step through this subassembly and just take a look at something. This is something that we actually use for real in projects. I did strip probably half of it off of the end. We can take a quick look at the one that we actually use for projects before we jump back to this one. It's the same thing, and it just has a couple shapes in here. This is a subassembly that was built specifically to be able to rapidly do earthwork when we have a alternative corridor that we're building as an alternative analysis to be able to understand the costs and impacts of something. So basically, we just push this retaining wall subassembly through very quickly anywhere that we think we may need a wall, and take a quick look at it, and it will drop these shapes in there, which tells us the excavation limits that are required to put the wall in place, as well as 3 different types of quantities that are able to be pulled out of this, along with a modifiable back grade, some other modifiable slopes, and toe and heel that automatically adjust based on equation per the height of the wall, and also whether it's a cut fill. So this is the one that we actually use in the project. It ends up being a little more sprawling. There's an extra conditional at the end and some other thing, 2 more conditionals at the end and some other things. But we're gonna take a look at one that's stripped down a little bit here. So what we have is a retaining wall that's inserted. So let's say there's a roadway up here, and we're doing the retained fill portion, and this if we take a look at this, you can see that the retaining wall just flipped from cut to fill there, depending on the situation that it's in. So it's the toe is going to be under the bulk of the fill, which is on the inside. If the existing grade is below the insertion point, or I guess not the insertion point, the face of the wall over here. AP1 is on the face of the wall, and if it's above, it's going to flip. It's going to flip the other way. We also have it so that the top of the wall is going to expand and contract with that. And if you notice, the toe and the heel actually get slightly bigger. For this. This is a chart that we were given by our structural engineers that we ran a regression line off of to be able to determine kind of the relationship between the height and the toe. If you ever want to see a structural engineer twitch, tell them you ran a regression line on a loading chart that they gave you. But these aren't for final design. These are for really rapid earthwork calculations. So that's the purpose of this one. It actually gets used in there, used on our projects. Up past 30% a lot of times as we're getting these out. It often gets swapped out with the significantly more complicated retaining wall subassembly that I showed you earlier. And we're just going to take a look, run through kind of the whole subassembly here and take a quick look at what it does, how these work, and then the branching back together. Just notice that we're always trying to come back together, and some of the reasons that we can't for some of these, and that when we can't, we try to always line these up very carefully and make sure that we number these exactly the same. In theory, you kind of know what points you're ever going to attach something else to, and that's really where the points matter the most, the numbers matter the most. In practice, I try to make it that every single point, if it exists in the same spot, always has the same number, so that we never have to deal with that. That dropping subassembly issue, it is mystifying the first time you see it happen, and it can be very hard to track down. So all we're going to do is start with a point right at the origin, where the wall is always coming in. And the next thing that we do is take a look at where we know the surface of the wall is going to be. The face of the wall is 1.5 feet over. Again, if you take a look here, absolutely none of these are going to have numbers in here, so that all of these can be modified when somebody brings us into Civil 3D. So the wall width is 1.5 feet wide, 18 inches wide, pretty standard placeholder. If somebody needs to modify that inside of Civil 3D, they should not have to open up Subassembly Composer ever. If you save Subassembly Composer and you re-import it, somebody else tries to rebuild that corridor with a slightly different version, it doesn't work. It's frustrating. You just want to avoid that. So literally any number that is ever used in here, I always use an input-output parameter that is modifiable by the Civil 3D user. And that actually includes the link codes and shape codes too, which is not really part of this presentation, but just as a best practice, highly recommend it. So what we do is we go from the insertion point and we go over to point AP1, which is a point on the surface, on the face of the wall. And this is going to ride with that existing ground. And we're going to use point AP1 for a lot of things. We're going to use it to set the top of wall. We're going to use it to see if the face of the wall on the outside, because we don't really care about the surface over on this side of the wall. We care about it on the other side of the wall. We're going to see if this is in a cut or a fill condition above or below that insertion point. We're going to use it all throughout this. So I'm going to jump to this decision here. Simple if-then statement. We are going to check if the y value of point P1, literally how far up it is as the corridor is building, is greater than or equal to, just greater than point AP1, the y value of point AP1. So if it is, then we're in a fill condition. And if it's not, we're in a cut condition. So as it clicks back and forth past that, we end up taking different paths here. So if we click on point if we click on point P2, we see it's that point P2. If we switch up here, we click back on point P2, we see it's the one on the other side. So in fill condition, we are simply at point P1. And never do a vertical line because the CAD doesn't like those, so we're very slightly off, and we go up by the height above variable, which you can set 1.5 feet up and over. On the other side, if we're in a cut condition, we actually just need to stay the height above plus some of the distances there, as this is starting to get bigger and bigger. So this is the reason that we can't branch back together right here. These 2 point P2s, even though they look pretty similar, do end up being in a different place. We won't step through all of the points going through here, but I do want to just get down to this toe offset point here quick. So the toe is always in front of the face, the heel is always behind the face for it, and just showing that this is literally a regression that we pulled out of Excel. Quickly and stuck in here as the difference between P3 and P4. So we literally pulled the height of the wall, P3 to P4, out, multiplied by that regression number, and added a 1.5 feet for the top of wall there. And not for the top of wall there, for as part of the intercept line. Same thing with heel, different equation, but the same thing. And then we once again, after setting those for both of them, jump back in. We actually are using the same decision in this one. We're checking to see if it's a cut wall or a fill wall before we split back out. So these are similar. The reason we came back together to do this is to only have to write that once. The reason we didn't put these further up is that we needed to understand what the height of the wall is before we were able to do the math to understand what the heel and toe are. So we needed point 3 and point P4 to exist before these, so we branched back together, and then we jumped back out. This could be made a little more compact. Some of the middle points are the same here in some of these stretches, and I just got lazy and didn't kind of come back together and do the decision again, 3 times, which would have probably been technically best practice. But yeah, we needed those points to be able to understand the height on that. When we came back together, and we're going to split right back out, and then you build the rest of the wall. And there are multiple ways to do this. We could try to talk through some of that, but as we're going, we just see that a point P5 here, and the link back to it is the toe offset. If we are in a cut condition, we see over here that it is the heel offset, and then we follow through the same thing. And as we come back together at the end here, point P9 is the heel offset, point P9 over here is the toe offset, and then we branch back together and we can build our excavation lines based off of these points, which are in completely different spots for it. So you see point 10 is based off of point P6. Point P6 is in a completely different spot depending whether this is a cut wall or a fill wall. But we can build these with exactly the same points and point numbers, point codes, and link codes very easily for both of these. So this is a very simple. It's not a complicated subassembly. Like I said, it's pretty compact, but it does a lot. It targets two different surfaces. It checks if it's in a cut or fill condition, and it builds a different shape completely based on whether it's in a cut or fill condition. And we're able to do that very simply, very cleanly, in a way that's pretty easy to follow, even if this wasn't your subassembly that you made. And it's very easy for somebody else to be able to use this subassembly inside of their corridors as well. So we're going to talk right at the end here just about variable rewrites, and I actually am going to open up the curb assembly that we use inside of our live production corridors. And this probably is going to look overly complicated for just being a curb, but I just want to show that you can do quite a bit with variable rewrites inside of Subassembly Composer as well. And so as we take a look at this is very similar to that ultra simple subassembly that I had on screen earlier. If we take a look down, it's a little more complicated, and part of the reason for that is that this has essentially every curb that MnDOT, again I'm from the other side of the river there, that MnDOT has is selectable from this particular dropdown. So you can do all the different B curbs that are easily available across the board on this. And as we change some of these, you can see it follows the plate exactly. And you shouldn't have to change any of the other variables as you're going through. There's also an insertion point on this one as well, whether it's at lip, back, or flow line. And just another one, just another drop down for where the insertion point is on this one. And so we can just drop this curb in no matter what we're going to be using across the board. It's incredibly flexible. The other thing is that it actually has a override, which is if we have type override, we have not available in here right now because we're not using the type override. But if you type any reasonable curb name in here, will be 612. You can see that it's going to snap down through there for it, and it actually gets parsed and turned into math. There's no real limit as long as you get that first letter right there for it. B636 I don't think exists as a curb for it, but it will accept it for it. So you can type in very nearly anything that the state of Minnesota has, and it will also snap in. And the way that is done is that it checks right at the start if the type override is set to NA or not. If it is set to NA, it just uses the dropdown. If it's not, then it uses what the curb type is set to. And you can see here that it goes through and it actually pulls out the numbers from the different widths, whatever one was set inside of here. So you can see that it sets curb type. It sets a variable. This is what I'm talking about with it. The variable name is curb type, and so this exact same variable can get set to two different things. Either the dropdown that we've got, and the value that it's set to, or whatever that type override is. And then we're going to only look at this one variable. So this is one where we kind of have an almost nested conditional inside of here. And it's going to change what the variable is set to. And once we do that, we're able to go in and we're able to pull out just pieces of that string and be able to set things like the height and the face slope for it using a chart that we were able to use off of just the standard curb plate. Check if it's reverse or not, where the attachment point is, some of the line codes and shape codes. Set the origin, we just have a simple switch inside of here. Again, that needs to be enumerated and set to be a string. And then we do the geometry. So these few points actually build the curb no matter what it is. And just wanted to point out that this is another option here. If you tried to do this with nothing but conditionals, you would have 30 decisions lined up, probably more, as you checked the type and the height and the gutter width, whether it was reverse or not, and the insertion point. If those all stacked up as branching conditionals, this would be a sprawling monstrosity. I would argue it would be literally impossible to do inside of Subassembly Composer. But when we rewrite some of the variables right from the beginning there, we're able to make it a nice, compact, streamlined subassembly that has every curve that the state of Minnesota uses in one nice, neat little package where you never have to worry about, typing the height in wrong, typing the gutter line in wrong. So. All right, that is it. Thank you, everybody, for attending. I went very slightly over there. Apologies on that. I'm happy to stick around and answer any and all questions that anybody has. I did go back and cut out a section on switches. They are essentially decisions like we went through multiple times there with more output parameters. I spent an enthusiastic 8 minutes in the middle of the presentation talking about those before I realized I was about 8 minutes over and they did not make the cut. So if anybody wants to chat about those real quick, we can. Also, feel free to send me an email if you have any questions on any of these, if you want any sample PKT files, the subassembly composer files for it, I'm happy to send those over. I love this stuff. It's my favorite part of working inside of Civil 3D. And I would love to geek out about it with anybody. If people have any questions, either to ask right now during this session or by email later on. Thank you so much.